Good afternoon, folks. Today we're going to be working on a presentation. Let me get into the show mode here. Let's see if I can do that. Right there. How to measure your lead acid battery bank capacity using an Arduino controller. This is a very cheap, uh, basically microcontroller is about $5 or less. And last presentation, I talked to you guys about uh, that I have about 3 battery banks, and that these two are about 7 years old, and that this is my newest, which is about 2 years. So there's, as I'm planning actually to reduce from 2 banks here, the 2 oldest, and pick the best battery and do only 1 bank. But in order to do that, I want to be sure that I take a look at the battery capacity that I still have within this bank. I know that it's not much, but I would like to know, something that before you start to, trash some of these batteries, you definitely want to take a look at it deep. They didn't cost me much. I mean, but again, it's just energy wise, why, trash them if they are still there's still some energy on them that you can really pull out. So with that said, you probably remember this diagram because it's basically of my 1400 watt solar system backup, which happened to have the 3 battery banks that I told you about it. At the beginning, when I installed this back in 2018, these 2 banks were about not good, fair. I would say a little bit less than fair. And this is my new bank, which is doing pretty much all the night shift recently. And if you want to see a little bit more about this presentation, you definitely can go to a previous presentation that I have on this backup system. So here's the 3 banks, as I told you, the bank 1 and bank 2. They are about 7 years old. In the beginning, when new, they were about 230 amp hours, and this is my new bank, which is 2 years old. This also about 230 amp hours. Remember, you don't use, even this system are about 230 amp hours. These are lead acid batteries. You only use about 40% of them. You don't discharge more than 50%. I would say that's the maximum, because you start to do that, you will damage the batteries, and they are expensive, so you don't want to do that. So what is the actual battery capacity? That's always a question. You start to use these batteries for a while, and you need to know what do you have, you see. So this a little story is how to measure the lead acid battery bank capacity. How to is we do what is called a loading test, which consists of installing a resistive load and to the battery bank and measuring the current to the circuit. You measure the current, the battery bank voltage, and the time through the discharging process. Okay. For example, for lead acid batteries, when you are discharging, I mean, a way to pick this resistive load has to do with this what is called the C20 discharge test. The C20 discharge test basically is, I mean, when your bank was new, that was about 230 amp hours, then just to calculate the discharge current, you then divide it by 20, and that gives you 11.5. This is the discharge amp. So you need to select a resistive load that will do this trick. This number or a little bit less, whatever is convenient for you. The C20 loading test is the typical value used to report the capacity of new batteries. That's how it's done. And very important, the working capacity is the actual capacity of the battery bank at no more than 50%. In other words, if you are trying to measure the full 230 amp hour, you will damage the battery. This is an estimate. You don't do that. I mean, if you want to know working capacity, you don't get more than 50% depth of discharge. That's how you do it. You never want to go above 50%, which boils down to, if you have what is they call a 48 volt battery bank, it boils down to never drop your voltage on your battery bank below 48.5. That's kind of the maximum, or said in another word, the minimum, I would say, in terms of dropping the voltage. This is typical. What would you do? You have your 8 batteries, 48 volt plus, and you do sort of a connection as I'm showing here, a positive going through a breaker, and then there's a meter, an ammeter, a clamp ammeter to measure the current, and it goes to something that can sustain a lot of heat. I mean, how about a heating element, right? You put this in a bucket of water, and the negative return back to the negative of your battery bank. You also need a voltmeter, something that is telling you what is the voltage, how's the voltage dropping as you discharge the battery, and obviously a timer. So you put all that together. When you close the switch, current will start to flow. This will get very hot, and you start discharging the process. So the idea is sort of like to have a table like this. This is how you might do this kind of manually. For talking about the resistance, the heating element, this one in particular is about 8 ohms. It's 1800 watts at 120 AC. That's how much heat it will generate at 120. And so again, looking at the table, like for example, if you close the break at 120, lapse time is 0 at that time. The volt of the battery is whatever volt you are reading here, 52.34. The amp hours are the sum. Probably the amp, it takes some seconds to get the clamp reading. This 0 might not be totally truth. You start to guess a number, probably close to 6.5. I would say within a fraction of a second. So let's say a minute later, you have the 52 volts well established here, and the 6.5 amp, and the amp hours, and so forth. So these are calculation. Again, these are kind of a calculation that you make based on average, you see, and so forth. And the sum is this: you keep adding this area as you go by. For example, one simple one will be, if you are calculating amp hour, this number here will be the average of these two numbers, right? That would be the sum of those divided by 2, and then multiply by the elapsed time, which is 1 minute, but you have to divide by 60 to get it in amp hours, and that's where the number comes from. And so when you are here at 125, the elapsed time, 5 minus 1, that's 4, and you multiply, you take these two numbers, you average them, basically sum them, divide by 2, and multiply by the elapsed time, divide by 60, and you get this number. So that's amp hours as it keep going, and the sum is just that's what it is. You keep adding each segment until you keep doing this in a table, and I bet you will not do this. This is basically, you take 550 minutes divided by 60. That would be around 9 hours. You will not do that. That's why we have another method, but this is basically the idea, and this is one of the reasons we don't do this like this manually, because it takes a lot of time, and eventually when you hit the 48.5, when you stop, this is the last number recorded, and you sum all of these numbers here, and for this particular case is saying that the voltage start with 52.34, it dropped to 48.5 within 50 minutes. That's a 57 amp hour capacity. That's what you have, and you might say, well, that's very low from the 230. It's not bad, actually. It's not bad. 57 amp hours. If you check the cost of lithium iron phosphate for a 48 volt at 57, we are talking, $500 still. So it's a very good number. Again, that's how you plan. This is how you can do it manually. The only problem here is waiting. I mean, you can, in fact, the current or the amps will not change much as the voltage drop very little from 52 to 48. It will drop a little, but not drop much. So you can be okay reading the amps and the voltage, time to time. It's just the problem is that you don't want to go below the 48.5. Okay, that's the problem of doing this manually. So the idea is, how about if we do that with an Arduino? This is perfect. The Arduino will do this trick very simple for you. This is in particular to measure amp hours and watt hours using an Arduino microcontroller. This is the Arduino. As I said, it's about $5 or less, depending on what type of Arduino you get. This is Arduino Uno, and with an LCD display. This picture is from a YouTuber that work a lot with this type of display. So I took this photo from him. I will provide credits on my description for him. Excellent video that he has about how to use the LCD screens display. Sorry for that. And so there's all the connection. I just took his image or picture and add few things, like for example, this here is the voltage divider, just to get the proper voltage from the battery bank, which is here. This is the battery bank that I'm talking about. You get a line here from here. There's a line here that I'm not showing that goes here, and from there, from this voltage divider, I get eventually in analog pin A1 the voltage of my battery bank. Very important is this piece here. This piece here is sort of like the breaker, and is under the Arduino control. When pin number 10 go high, it close this solid state relay, and when it close this relay here, and then you get current going through the heating element and back to the battery, and you complete the circuit and you start the discharging process of the battery. So all the information that you are getting, like voltage, amps, and amp hours and watt hour, are shown right here at the LCD screen. You don't need anything else. That's the nice things about it. All right, so let's see. Wow, now this is very important. In trying to understand what we're doing in the Arduino, we need to know a few things. First of all, is the data acquisition process, and we are picking two. If I go back once, I'm picking two, the A0, which is the reference voltage, and I'm picking also the A1. The A1 is the true voltage here at the battery level. What voltage is the battery system as you are discharging the battery. So right here, when you close the Arduino to do the study, he start to crunch this analog, getting the analog data right here. This is the time it takes, and when it reports is when it finished. Then it start to display those numbers. It take a while for display those numbers, about 4 seconds or so, and then it goes back to crunch more numbers, and eventually it will display the numbers. So when it finish here, you got the first point. This is like, for example, amp calculation, and when it finish here, you get the second number. That's the second amp calculation, and eventually you get the third, and you keep going until the voltage dropped to the cutoff voltage, which we are saying that is 48.5. So what is important here is what we call the elapsed time. This elapsed time is the timing, or the amount of time that it took from one reading to the next reading and so forth. So that's very important that I got that number as, as perfect as I can get it, just to ensure that I got a good precision during the integration. Because the area here, the area under this curve, eventually is the one that we are talking about, what is amp hours, for example. Here a little bit more, so you understand what is amp hour calculation, which is called the area under the curve for amps versus time. I have amp here and I have time here. Like, for example, I got this 3 point as to show you, and this is what's called the first area. This is the second, and you will go third, fourth, and so forth. And the method that I'm using is called trapezoid method. Basically, is the area when you have two different heights and an equal distance. So you have the average of the height, h1 plus h2 divided by 2, multiplied by the distance, that give you this area, right? And you do the same for this area. So I'm doing that for you here, just so you take a look at it. What I'm talking about here is that, for example, 10.25, that was the first, this point here, times 0. And then 3.41 seconds later, I got a 9.17. So that's the average between those two multiplied by the elapsed time from here to here. That's 3.41 minus 0, right? This minus this. That gives you 33.1 amp second divided by 3600. That gives you this number in the proper significant figures. That's 920 times 10 to the minus 3 amp hours. I will do the same with the second area, which is the 9.17 and the 6.15. I average those, multiply by the difference, and eventually give you 7.26 times 10 to the 3 amps hours. So if I want to know what is the capacity of my battery at time t2, which will be like 6.82, that will be the sum of this plus this, right? You keep adding, and this is how the process goes. Okay, now to understand a little bit more about battery discharging process, what is really happening. Batteries typically have a curve like this. They pretty much the voltage drop a little bit, when you start to pulling energy from the batteries, but then it will stay there for a while until it eventually get to a point, like for example this 48.5, that we call it the 50% discharge on lead acid batteries. So we don't want to go more than that, because after that the battery voltage drop quite rapidly. So you want to stay here at the 48.5. Now on the other hand, the amps keep steadily dropping, but very little. They pretty much stay like a straight line. Okay, in fact, you could make it like a rectangle here, and like for example, if I said that the amps is about 10, and the average amps from here to here, it average about 10 amps, and the time is 10, that's amp hours. It's very simple. It just will be 10 by 10, 10 on the amp on the high, because it's a rectangle. The high is 10 amps, and the length of this rectangle is 10 hours. So that 10 by 10, the amp hour for this, for example, this is an example, would be 100 amp hours. That's a decent capacity. Okay. And how about watts? Well, watt is another function. That would be like multiply voltage times amps, you get watts, and pretty much you can calculate then the energy of a battery by doing so. All right. And it's the same concept, nothing more to it. And the idea of doing watt hours as well is because it's allowed me to, for example, I will show you. Let's see if I have it here. Yeah, I do. Battery capacity measurement. I'm using here. Actually, this is from a capacitor being discharged. Okay, and one thing that I'm stopping right here at, for example, at 48.5, as I told you. And as you can see on the gray line is amp versus time, pretty much constant. You read that here in this side, amp hours. So it started about a little bit about 6, and it end up, if I'm talking here, very close to 6. So it averaged about 6. That's it. That's the amp through the discharge process average about 6 amp, and the time about 48. That's 9. That's about 9 hours. So I will say that if I made a cut at 48.5, that will have about 9 hours times 6. That's 54. amp hours. That's the capacity of this capacitor at if I stop at 48.5. If I let it go, then more energy will have available. Capacitor are a different animal, I would say, in the sense that capacitors can be discharged deep, deep, deep. I would say to zero to recharge them and reuse it. But that's another story. I mean, capacitors are like I would say top of the line of term of battery design. I mean, if you are designing, let's say, spaceship that need to go to somewhere where uh, energy is critical to do everything that it needs to be done, and obviously, and you can only reach that every 10 years. You want the best of the best type of system that can, with no maintenance, endurance, uh, all the space condition. That would be capacitors. Definitely will do that. They will charge daily basis and no question asked. That's what they are designed for. In fact, I think last time I saw a capacitor, they have, I'm talking about what they call a supercapacitor. I think that they have what they call a charge discharge cycle of over 100,000. That's a lot. I mean, you're talking about, like, for example, lithium iron phosphate, they get close to 5,000. I mean, we're talking about a capacitor, a supercapacitor with 100,000 charge discharge cycle. That's a lot of years, my friend, a lot of years. So this is the battery capacity measurement. I mean, I'm using capacitor for testing, and this is how it looks like for the Proteous simulation. I'm using a capacitor here. I close this to charge the capacitor. To charge the capacitor at a given voltage that I want, like for example 60 volt, that would be the maximum. And here's the Arduino, and here's the relay that I'm talking to you. I'm using a mechanical relay. Actually, if I go back for a second, this is a solid state relay. There's no solid state relay in the Proteus simulation, so I end up using a mechanical. I could make one with the parts on Proteus, but that would be another project altogether. So I said, let's use a mechanical relay. I don't care. And when you are ready, it will energize the solenoid, and you will close this circuit, and you will discharge this capacitor right through this resistor, which is about, look like a 5.76 instead of the 8 ohms. That's a different resistor. It doesn't matter. You use what you have. And here's the LCD for sending all the information, time, the amps, the voltage, the amp hours, and the watt hours. So you send all that information here, and you let it go. This is how it works. You let the Proteus do the simulation for you. And I don't think that I have anything any more to say. I really appreciate you be with me up to here. So let me show you now the simulation in Proteus, how it looks like. Good afternoon, YouTubers. Again, let's see. Let's take a look to what we're doing here. Let me launch Proteus here, and recent project, battery capacity. That's it. Here we are. This is actually, let me put this right on the center if I can do that. There we go. All right. This is the simulation with Proteus. Actually, as I was telling you, I'm going to be using capacitor for my simulation, just to simulate batteries discharging process. I'm gonna be adding. I just add this kind of a fuse here. It's kind of nice to have it. And there's a little bit of a difference here. I'm using a mechanical relay instead of a solid state relay. Just is for the Arduino, I mean for the Proteus simulation. I couldn't get a solid state relay, so I mean you could make one, you can build it yourself with all the parts that there is in Proteus, but don't do that and focus in what is important, which is having a relay to close when you are gonna discharge the capacitor. All right, and this is the heating element. It's a 5.76 ohm. This is a 2500 watts heating element at 120 volt AC. So that's what this 5.76 come out. Now I have here the LCD liquid crystal display with all the connection that I talked to you about it. Right here is the voltage divider. It's about, this is 14k ohms resistor with 1k ohm resistor. So when I charge this capacitor to about 60 volts, the voltage here will be about 4 volts. And here is the reference voltage, which is go to analog pin A0, and A1 is the one that read the battery voltage as through the discharging process. One important aspect is that I can close, if I get my, there, I close this switch. When I close that switch, this battery, which is a 60 volt, will charge the capacitor to a 60 volt. The idea is that this battery obviously does not exist. It's just to charge the capacitor to 60 volts. And from there, I open them up. I open this one and then close this one. And then is when the discharging process start. Let's do that for a second. Let me close here. Let me open here. And let's run. Let's see. Oops, a little bit, see, okay, there's a problem. The problem is that I closed a few minutes ago, I closed the Arduino IDE, and obviously it couldn't find the hex file that is looking. This is the compiled file for the code. So let me go here for a second and let me open my Arduino IDE. So opening the Arduino, take a few minutes, a few seconds I should say, no more than a minute. And so let's see, there it is. This is the code. I will explain the code later. What is important is that I'm gonna let's see, what should I do now is I'm gonna compile it. And there we go. Now after that, one thing that I should do is copy the compile file, which is this one here. Control copy, and then go to my Arduino here, double click just to ensure that everything is right. Let me erase that one there and put the new one. It shouldn't matter because it has the right reference, but anyway, let's do it again. I hit OK. Now whoops, change my page again, bring me back. There we go. Now what should I do is close this, have this closed, and have this open. So if when I close this, because I don't need it, if I launch now my Proteus simulation, it should work fine. Perfect. Now I got battery capacity on the LCD display. I have the 60 volts. The capacitor is charged to 60 volt, and as you can see, this is open. I mean, it's not doing anything. I'm not discharging the capacitor. It's waiting for me for this to occur. So what I'm gonna do is open this and now close this. Oops. I don't know whether you saw it. It's kind of interesting. I blow the fuse. I'll be damned. It blow the fuse. It's a 20 amp. Well, that's what I wrote. Let's see what is actually inside here. As you can see, the voltage is not dropping. although the relay, mechanical relay, is closed, but I blow the fuse. So nothing is really happening. You can see some reading here, but the voltage is not dropping. And those are the first reading that I have from the beginning. So um, that's basically it. There's a problem there. Let me stop for 1 second and let's figure it out what's happening here on my fuse. Oh, no wonder, it's 1 amp. Oh, I forgot to change it. It's a 20, it should be a 20 amp fuse. That's interesting. I thought that I changed it. Well, I guess not. It's a 20 amp fuse. I think that I wrote it, but never changed it inside. So now I got and it's interesting because it's Proteous is using an active. It lets you know when things really blow up, and this one blow up. Okay, so now I got a 20 amp fuse, the way it should be, and now I should start again here, open this one, and run this one. So I got again battery capacity. I have to open this. Now when I close this, actually it's a 10 Faraday's capacitor. That would take for a while. Let me stop it here for a second. That's gonna take a while. Let's drop this to, I don't know, 1 Faraday. That would do. It's small. Let's close it again. Let's have that open and let's run it. It's 60, and now open this and now close this. See how quick is discharging? It's a small, I mean, 1 Faraday is still big, but for this issue here, I'm reading that. Let's see, I'm reading what hours, amps are dropping. And so the voltage, and let's see what's the area that I got for the watt hours. Watt hour 0.56, maybe it might hit 1 or so. 359. Let's see, when I hit about a voltage here, I will stop it just so that will do some calculation about the energy contained in this capacitor when it was about 60 volts. Pretty much to see. It's about watt hours, 0.57. Might add up to 0.58 eventually when this goes to 0. Let's see one more. 57. So let's keep it running. Let's go to a calculator here for a second. And let's see, numeric calculation. Whoop, there we go. I like this calculator speak. So let's see. I have 1 Faraday capacitor. That's one. I just have it there. Divided by 1/2. Multiply by the voltage was 60, and that 60 was square. Whoops. 60 volt. So I mean, this is the capacity, one Faraday. 1/2 is part of the formula. 60 volts square. Let's hit equal. That's 1800. That number needs to be divided by 3600, and that's 0.5. That's the energy in watt hours that I should be showing. Showing a little bit more than that. Let's see, it goes to Proteous again. 0.57 is 0.07. 0.07. Higher than what it should be. Probably an integration factor that need to be kind of a fine-tuned, but it's doing okay. So I got that number. So let's stop here for a second. Let's stop, and now let's increase this to, I don't know, 5F. So do the same process. Have that close. Open this one and run. Now it's charged. Have this open, and now close this one, and you are discharging. You saw this how it changed from here to here when you close, and now you are discharging the capacitor as the first timing. It goes again. And let's see, that's a 5F. Let's go to the calculator again. Let's see what would be the energy. It's 1/2 multiplied by 5 multiplied by the voltage 60, that's square, and that's 9,000 joules divided by 3600. That's 2.5. 2.5, that number will be watt hours. That's the energy within that capacitor. So let's see what the Proteous is doing. It's still 2.0A and it's still adding. The voltage is still high, 21.1, and dropping, still high. So I guess we'll have to iterate for a little while, just so that that number get down to what it's supposed to be. Let's see. Anything else that should be important here to mention? Not really. I guess that I have said it all. Already, and I think we could do is go to the code until this keep crunching number here. Although it's pretty much done. Let's see. It's almost about 11 volts and dropping. Still the current. Let's see what the number we are heading. 11 voltage 11. The amp hours 0.07 amp hours, and the watt hours 2.47. Yep, it's hitting, or it's going to the eventually to the 2.5 mark, which it should be. And let's see. I don't know whether to stay here any longer. Because what I will do here, it hit the 2.5. Still got some voltage, some current, so it will end up a little bit higher than the 2.5. Probably need to tweak a little bit more the elapsed time, just to ensure that I got that perfect. It's 2.53, so that it got already 0.03 above the 2.5 mark, as we got from the calculator. This is watt hours, and so let's see, 4.7 voltage, amp hour 0.08 amp hours is that's the capacitor system, and energy is 2.54. So I got 0.54, about 0.04. I would say this will end with 0.05. Let's go to the calculator for a second. So I end up with 0.05 above 2.5 multiplied by 100. So that's an error of 2%. Okay, that's what it looks like. I might need to tweak a little bit more the elapsed time, the integration factor. So let's go back here to Proteous. Let's see, voltage, hour 0.08, 2.55. Yeah, now I'm in the 0.55, 0.05 above, about 2% error. Actually, let's stop here and let's change this to, I don't know, if I put 10F, it's gonna stay for a while. I mean, that's for sure. Imagine 100F. Wow, this simulation run pretty much in real time. Let's put 10F, and that's it, and we quit from there. 10F, and we close this. Oops, and open this one. There we go. And now charge the capacitor. we are ready. Now we are ready to discharge. We close here, and there we go. That's time 0, and now it start to iterate, and that will take folks for a while. I mean, you can see how slowly the voltage is coming down. It's a large capacitor, 10F at 60 volt. Let's see what's the energy there. Let's see, 60. So I said 1/2 times 10 times 60 square. Energy wise, that's 1800. Yeah, 18,000 joules. That divided by 3600. That's about 5 watt hour. So with that said, I guess what we should do now is let's see how Proteous is doing. See what the number we are getting here in terms of watt hours. 3.19. Well, slowly getting there. So let's take some seconds, and I'm still tweaking the code a little bit. So the important thing here is eventually I need to add this voltage cut. I haven't added because I'm testing it with using capacitors. I want to drain the capacitor to the fully so that I get the energy and eventually the watt hours, and I can compare with the capacitor discharging formula of energy content. And heating element 5.76, no problem there. Then I keep there's some variables here, but the most important is this elapsed time. Very important I have that right for my integration. And in the beginning, I used to have this data being sent to a terminal, not anymore. So I still have this here just in case. Pin 10 and pin 9. Pin 10 is to close the relay. Pin 9 is to let the Arduino that we are ready to start. And here is the liquid crystal display, which is a 16 column times 2 rows. And the first instruction that I have is battery capacity. We're gonna be using, that's what we're gonna be doing. And if the pin 9 is closed, then it closes the relay and it starts to do all the Arduino stuff. In this particular case, is the gathering of the analog information, the reference in A0 and the voltage in A1. After that, it start the timer for the elapsed time, and it do a series of stuff, and after that you get some calculations. Battery voltage multiplied by 15. 15 is just the voltage divider, and you get the amp calculation, the watt energy. I mean the watt, you need watt because basically you need for the watt hours you are averaging the new watt in the calculation versus the old point that you have. So you average between those two for the trapezium or the trapezoid type of area calculation, and eventually you get amp hours and watt hours, which is a summation of all those areas. And as I said, I have the terminal, VT terminal, not anymore. So eventually you start to write everything down to the LCD display, and it's here when you have the timer 2 again. This timer, the difference between these two timers, pretty much the elapsed time. I have this as a kind of a fudge factor that I used to kind of tweak a little bit more the precision of the elapsed time, just to improve my precision during the integration process. Anyway, that's the end of the story. That's the code, very simple. Eventually I need to implement the V cut voltage. I haven't done it because I'm using capacitor. on Proteous. Let's see what Proteous is doing at this point. 127 amp, 1.18, voltage 6.82 dropping, and amp hours 0.15 amp hours on this 10 Faraday capacitor. And let's see what hours. Oh, I missed the watt hours. Let's see. Amp hours. Watt hours. 5.05. All right. 0.05. 0.05 might drop to our 0.06. Let's go to the calculator here. So it's going to be 0.06 divided by 5 times 100. So the error is 1.2% on that. So as the capacitor gets larger and larger, probably this error will drop to very, very insignificant value. I mean, who cares if it's 100 amp hours versus 99.5 amp hours? I mean, that's a large bank. That's a lot of energy contained within a battery bank. So certainly I can go stop here and do. This is what I would do. I will stop here. Let's see one more. Let's see where we are here. 389 on the amp hours, 0.16 on the watt hours, 5.08. 5.08. More or less. So it's pretty much done. So let's stop. And now let's put here a big one. But we would not, I mean, I would not follow it. This is what I would do. I put 100 there, close it here, open it here, charge the capacitor, open it now, and close the capacitor. And that will take a while. And when I said a while, it will take many minutes to discharge that capacitor. So this is what I will do. I will go here for a calculation, just so you know. I think that I put 100. That was the number. Yeah, it was 100. Wow, 100. So 100. So the formula is 1/2 times 100 times 60 square. That's 180,000 joules, and that number needs to be divided by 3600. So we are expecting 50 watt hours. That's what we should see when this is pretty much done. So hours so far 0.06, watt hour 3.46. That number should be 50. So with that said, we gonna do a stop here for a second and keep recording later on when it's pretty much done. Let me pause. Oh well, let's see. After a while, we are 1/1300 second or so. Amp has dropped to about 1 amp, and the voltage is still 609, and the amp hour 1.53 ampere hour, the watt hour 50.64, 0.64 above the limit of 50. Probably get to about 51. That's it's pretty much the amount of current, about 1 amp going down still. Yeah, looks like we might hit the about 51 watt hour instead of 50. So if I take the calculator out, let's see, that will be 1 above 50 times 100. Yeah, 2% error on that calculation. Not bad, no bad. I can improve. I can certainly improve that, and I will. But that's basically it. I mean, let's go back here. And with that said, I think that we're done doing the simulation, and everything that I want to show you guys is pretty much what I have so far. Thank you for your attention. Bye.